Good day, ECO235 students, and welcome to the final week of online lectures for ECO235. The topic that we are concluding this week is integral calculus, and the specific topic is definite integrals. So we've done this topic over the last 2 weeks. The previous week you dealt with indefinite integrals, and what you ended up with was a function itself. But with definite integrals, we are going to see that you in fact use it to solve for the area beneath a curve. So the prescribed readings is section 10.2 of your U textbook, or this is an additional text that you may use, the Jacques textbook, section 6.2. So as I said, last week you dealt with the meaning of integration and indefinite integrals. This week you also have a short MCQ test where you need to show that you are able to get your indefinite integral of a function. Now this week we'll look at definite integrals, and the application thereof that you need to be able to do in the exam is to use definite integrals to derive the size of consumer surplus, producer surplus, and if you were to sum these two, obtain your total surplus. Now, definite integration, as I said, is used to derive the size of an area below a curve. So here you have a curve. So to get the area below the curve, but above the x-axis within a particular range of x values. You have been calculating areas quite extensively in microeconomics, ECO 231. So it could have been the shape of a triangle, rectangle, square. In some instances, you needed to sum the areas or work out the change in areas in chapter 9, for instance, of micro. What made it easy was that the functions were linear or straight line functions. But what if a function is nonlinear, as you can see in this case? How do you go about determining the area below a curve? So the definite integral represents the area under the curve f of x between x equal to a and x equal to b. Now, a and b is what is known as the limits of integration, and it is assumed that a is always less than b, as we can see here. B is referred to as that upper limit of integration, and A is the lower limit of integration. So the notation for your definite integrals, it looks similar to the notation of indefinite, but we have an upper limit at the top of this curly long S, this integral sign, and we have a lower limit A. And of course, these would have values. So this is the notation for your definite integral, and it tells us that the definite integral of f of x between x equal to a and x equal to b is equal to, notice now we've got a capital F of b minus f of a. So remember that f of x, if you had that capital or uppercase f of x, that was the indefinite integral of this function here, f of x, right? So what we end up doing is we get the indefinite integral, but then we evaluate at the upper limit, and then we subtract f of a, the lower limit, from the upper limit f of b. So as I said, the evaluation of the integral between these two limits, your upper limit and your lower limit, your first step is going to be to integrate the function. So remember, when you got your indefinite integral of f of x with respect to x, you got f of x plus c representing that constant of integration, and this was your indefinite integral of this function or your antiderivative. Step 2 is then the part where you need to determine the area underneath the curve between those two limits, the lower limit, which was x equal to a, and the upper limit, where x is equal to b. And it is derived as follows. So once you get your antiderivative, or you integrate this function, we need to evaluate it at b, and then we need to evaluate it at a, and then we say we then subtract the f of a from f of b. Now the constant of integration is going to cancel out when you subtract these two. So let's look at some basic examples. Here we need to get the definite integral, and I know that because I've got my lower limit and my upper limit, it's given, so I need to essentially determine the area beneath the curve between the values of x equal to a and x equal to b. So for all of these, the lower number is your lower limit of integration and your upper number is your upper limit. So therefore, you know, if you are first going to integrate this, this is simply going to be 3x. From last week, your rules of integration. So this is simply 3x. Now, this is the standard notation that we use when calculating the area beneath the curve using definite integrals. So you place the function, the antiderivative, in the square brackets, and then you have your upper and lower limits on the side. Now you're going to evaluate the indefinite integral at the upper limit and the lower limit. So f of b minus f of a, so that is b, and this is a. So now if I just solve, I've got 3 times 6, it's 18, minus 6, that is going to give me 12. So therefore I know the area below the curve between these two limits is going to be equal to 12. Let's look at another example. Here I have my definite integral of 8x between the limits of x equal to 2 and x equal to 6. So therefore, the indefinite integral of this is going to be 4x squared. So I know that because I would say 1 plus 1, n plus 1. That would give me 2. And then remember, you would say this coefficient times 1 over n plus 1, and n plus 1 was 2. So 1 over 2 is a half times 8. That gives you 4. So hence you have 4x squared. Remember, this is your antiderivative. So if you differentiate that, you should get 8x, and I can check 2 times 4 is going to give me 8. X to the power of 2 minus 1 is just 1. So remember, this is now your antiderivative, or this f of x is the indefinite integral of this function f of x. And now we are going to evaluate this at our lower and upper limit. So we first evaluate it at the upper limit, then we say minus the lower limit. So therefore, if you substitute 6 in first and then you substitute 2, then it's going to be 6 squared is 36 times 4, minus 2 squared is 4 times 4, and you should get an answer of 128. And again, this gives you the area below a curve. Here we again are going to get the definite integral of f of x between the limits of x equal to 0 and x equal to 2. So first you're going to integrate that. So here we've got x plus 1. So you're going to do these, treat them as individual functions. So x is raised to the power of 1. So 1 plus 1 is 2. So therefore, I would have 1 over 2, which is a half, x squared. And this is simply going to be x, and this is using your rules of integration. Now we are going to evaluate it at the lower and upper limit and say f of b minus f of a. So you first evaluate at the upper limit, which is 2. So substitute the 2 in wherever you see the x, and you solve, you'd get an answer of 4. And now if we evaluate at the lower limit is 0. So it's just going to be minus 0. So the area below the curve between these two limits is 4. The final simple example, again, we have to first integrate this function before we evaluate at the lower and upper limit. So therefore, if I treat these as individual functions when I integrate, here n is 2, so I have to say n plus 1, so it's 2 plus 1, it's going to give me 3. But then I have to say my coefficient times 1 over n plus 1, and n plus 1 was 3, so it's 1 over 3 times 6, which is going to give me 6 over 3, which is simply 2. So I have 2x cubed, and this is simply going to be 5x. Remember, the integral of a constant k is simply that constant times x. So now that we have our antiderivative or the integral of this function, now we can evaluate at the upper limit and the lower limit. So we first evaluate at the upper limit and then subtract the lower limit from that upper limit. So substitute the 3 in first. So I've got 3 cubed is 9 times 2 plus 5 times 3 is 15. That's going to give you 69. And now you evaluate at the lower limit, f of a, and you substitute the 1 in wherever you have the x, and you're going to get 7, and 69 minus 7 will give you 62. So again, it gives you the area below a curve between the following limits. Now you are going to be required to use definite integrals to solve for your consumer and producer surplus and total surplus. So in microeconomics, you were taught how to solve for consumer and producer surplus, but it would be for linear functions. But what if your function is non-linear, so not a straight line, a curved function? So therefore, the application of definite integrals is used to derive the size of your consumer, producer, and total surplus. So assuming the demand function is P is equal to F of Q, while the supply function is P is equal to G of Q at a particular equilibrium price, P star and Q star, then your consumer surplus is going to be equal to the definite integral of your demand function with respect to Q between the limits of Q equal to 0 and Q star, which is your equilibrium quantity, minus the product of your equilibrium price and equilibrium quantity. And then your producer surplus is going to be equal to the product of your equilibrium price and equilibrium quantity minus the definite integral of your supply function G of Q with respect to Q between the limits of Q equal to 0 and Q equal to Q star, which is the quantity at equilibrium. And once you have your consumer and producer surplus, your total surplus is just the summation of those two. So in the next audio, we will go through some examples thereof.